was praising so much. So we're going to hear a little bit from her about the theory of Kilonovae. Did it disappear?
It disappeared. Oh,
Okay.
Okay, I just want to sell it.
Okay, no. Yeah, it looks like it's starting to come out there. So let me, maybe if I take, all right, let's
Okay.
try to mess it up.
No, I know, it was already.
It looked like it was actually loose and tight. It looked like it got moving around.
Yeah, if we just do this, so it's less. Sorry, guys. Okay, here, I'm gonna hold it like this. Do you want to try to like screw it in? I know that doesn't usually work, so I'm gonna let it in. I think now you're screwing it in. I think now it's, yeah. Okay, let's just like let go of it there. Okay, sorry about that. Yes, so I am Jennifer Barnes, and I was asked to talk a little bit about the theory of Kilonovae. And I'm thrilled to say that for me, at least, this is the first time I can talk about the theory of Kilonovae when that theory is somewhat backed up by observation. So it's an exciting new frontier in Kilonovae studies. Okay, I know it's the end of a long day, but I think fortunately most of what I'm going to say has been covered to some degree or other by other people, so hopefully this will be a useful synthesis to sum up everything that we're thinking about theoretically, and then we can move on to thinking about implications and what's going to come next for us. Okay, so right, the weird thing about Kilonovae that makes them so tricky to understand and try to predict their signals is that they're powered by the R process. Unlike supernovae, whose power source is dominated by the decay of nickel to cobalt and is like powered by a really well understood single isotope. In this case, we have this kind of weird, messy nucleosynthesis process, right? So the R process produces roughly half of the elements heavier than iron, and it only operates in really extreme conditions. So I have a very schematic picture of what happens during the R process here on the bottom of the panel. You have a very high free neutron flux. That free neutron flux is captured onto seed nuclei. The time scale for this neutron capture is very, very short. It's so short that you create unstable elements, but they don't have time to beta decay towards stability in between neutron captures. Instead, you work your way up the very neutron-rich side of the chart of the nuclides, and you end up in this heavy neutron-rich region. Then finally, once the free neutron flux has been depleted, the nuclei have a chance to sort of walk their way back down to stability. And then in the course of this restabilizing, they undergo decays, so much beta decay in this case, and they release energetic radioactive particles, and these heat the ejecta, and then the ejecta glow. So because they're powered by the R process, Kilonovae have a unique composition, and so we need to make sure when we build models of these things that we do a very good job understanding the optical properties of the elements in this composition. We have to know what the interaction of light is going to be with this particular matter. They also have a unique nuclear power source, which I'm not planning to discuss in as much detail as the optical properties, but I think it's worth pointing out that because you have all of these different nuclei contributing to the radioactive decay heating, instead of a simple exponential like you would get in the case of nickel plus cobalt, you get more of a power law. And so the radioactive heating can look very different, and we think this is probably important, especially in the late time-light curves, as you move away from the photospheric phase and you start seeing the full tail of the light curve. Okay, if you want to see the R process in more detail, this might look very familiar depending on how much attention you were paying to Daniel's talk. But here's just a movie of what happens. It should be a movie of what happens. Let's see. Right, so the R process turns on. We build up some seed nuclei, we hang out in this will they, won't they regime for a while until some critical threshold is reached, and then, you get a sudden whoosh up, building up these very heavy neutron-rich elements. Then we basically run out of free neutron flux, and from here we aren't really, the evolution of the composition isn't driven by neutron captures, it's driven by this decay towards stability. And of course you get this, as we said, a broad range of nuclei that are produced that's going to give you a lot of different decays contributing to the overall heating. Okay, so let's zoom in on this abundance really quickly. One thing about the R process is that the yields aren't, I don't know why I still have this movie icon in the bottom corner. Sorry about that. The abundances are not guaranteed. So what you get at the end depends on what you put out in the beginning, or what you put in the beginning. And depending on what you start with, the final abundance that you get can look very different. So we're showing scaled solar abundances in these red dots, and then we're showing the final abundances for the R process for a set of initial conditions. These were calculated using Jonas Lipner's code Skynet. Right, and so there are a couple ingredients that go into any parameterized simulation of the R process. So one of them is the expansion time, just how quickly is the system expanding, because that of course affects the ability of these seed nuclei to capture the free neutrons. We also care about the baryon. That's generally like a proxy for density, because a lot of the development of seed nuclei is driven by three-body interactions. So how effectively you're able to make seed nuclei is important for figuring out your final abundance. And then a big thing that we need to think about is what the electron fraction is going into the R process. So the electron fraction is a measure of neutron richness. So it's inverse to neutron richness. The higher the electron fraction, the fewer free neutrons you have around. So in the event that, I guess, YE maxes out at 0.5, we think, and that would be like equal numbers of neutrons and protons. So under those conditions are basically the conditions that you have in a supernova. So if somehow you tried to turn on the R process with a YE of 0.5, you wouldn't really get the R process at all. You would end up burning to nickel 56, and you would create a little mini supernova. But we don't think we ever reach conditions that extreme in a neutron star merger or a neutron star black hole merger. Instead, we think that we're likely to have lower YE ranging from 0.01, which is kind of an extreme low YE case, all the way up to about 0.25. So the lower the YE is, the more free neutrons we have around, the higher our neutron to seed ratio is, and that means each seed nuclei is able to capture that many more that many more neutrons and become a lot heavier, and that allows us to populate this heavy mass number region in the final abundance pattern. But if we start dialing down the free neutron number and then we get fewer neutrons per seed, you start to have to, you end up losing your ability to produce these very heavy things. So you don't suffer too much going from like 0.01 all the way to 0.19. These yellow and black curves look actually fairly similar. But in the calculations that Jonas and Luke Roberts did in these systems, they identified a YE of 0.2 as kind of a critical value. So if you can keep your electron fraction below that level, you do a pretty good job building up most of the heavy elements. But if your neutron fraction drops below that, you start to lose robustness in the R process. So you have a much harder time making the third peak elements, for instance. Okay, so I've been talking about free neutrons per seed. But if you rip apart a neutron star, you would expect generically there should be a lot of free neutrons per seed. So what conditions would give rise to a situation where you have these higher YE fractions? So there are two ways that I can think of off the top of my head to turn a neutron into a proton. One is just to wait, because a free neutron will decay, but it decays on a much longer time scale than the time scales of interest for this problem. So the other thing that you would do is throw neutrinos at it, and weak interactions will change free neutrons into protons. That's going to change your YE, and that's going to affect whether you end up with the very heavy R process material, with lighter R process material, or in a really extreme case with these iron group elements, that's going to be a transient that looks like a supernova. Okay, why does it matter, whether we, as long as we're making the R process, we think the energy input should be roughly the same, because either way, your decay heat or your energy production via decays is still driven by a broad range of nuclei. So why does it matter, if we're in this regime or this regime? And the answer is it matters because of opacity. So this is, I think, thank you to Ryan for giving a great introduction to this. We talk about our process opacities a lot, and that's really an overgeneralization. As was mentioned in the previous talk, the question is not, are we our process or are we not our process? The question is, are we able to build up a significant number of nuclei that have lanthanide opacities? So lanthanides and actinides are these elements that have their valence electrons in an open half shell. So you can see very crude schematics of what these atoms or ions might look like. We assume, if you think about all of the inner electron shells being filled, then you have some population of electrons sitting in the valence shell. And these electrons can, bounce around within the valence shell, which is going to change the energy of the atom slightly. And so these different energy configurations, hopping from one to another, is an energy change that is like an absorption. Sorry, that was not well said. What I want to say is that a photon can activate these changes, right? It can come through, it can be absorbed by an atom, and it can cause that atom's electrons to jump up to a higher energy level of configuration. And then the atom might readjust, most likely via fluorescent processes, and it's going to re-emit these photons. So, zeroth order, right? The likelihood that any photon is going to get absorbed by an atom as it travels through the ejecta, being redshifted as it does, is proportional to the number of possible lines it can be absorbed by. So in the case where you have more atomic complexity, like we find in these elements with open F shells, there are a lot more possible energy configurations. Just that's a combinatorics argument, right? There are more ways to move the electrons around, more slight differences in the electronic energy levels. And that means that there are also more ways to transition from one of these to another. And so, so the critical, I guess, criterion for whether or not we get this high opacity is not really, whether we have the R process nucleosynthesis activated or whether we reach a certain mass number. It's really how well represented in the composition these lanthanides and actinides are. And that's what's illustrated in this plot here, which is showing expansion opacity based on synthetic data. So I think one of the major themes that has emerged today is that we do not have the data that we need to experimentally identify particular lines or to identify particular spectral features. But what we have gotten pretty good at doing is using atomic structure modeling to get a good understanding of statistically where the strong lines lie in wavelength space for different kinds of elements. And we're able to do that with atomic structure modeling. And once we know the lines, levels, and oscillator strengths that are associated with different ions, we can use those to construct an expansion opacity. And then that is kind of the critical ingredient for radiation transport. So here we're showing a collection of elements that we think will be produced in the R process, along with iron for comparison. And you can see that these open D shell element, which is an ion of osmium, looks pretty similar to iron too, whereas cerium and neodymium have opacities that are much, much higher. And the discrepancy between the two is particularly apparent as you go into longer wavelengths. Right, so I think the critical point here is just that atomic complexity is the thing that drives the high opacities that we expect to be present in the lanthanide rich ejecta. So the key ingredient for understanding the nature of Kilonovae emission is probably going to be, or should be, the mass fraction of lanthanides present in the ejecta. And this is just showing, that was an argument about opacity, this is showing the effect that opacity has on light curves. As you might expect, when you crank up the opacity, it makes it harder for photons to diffuse out. So this results in a longer light curve and redder spectrum. So these two plots show the results of radiation transport simulations for two systems that are the same in every way except the composition and the resulting opacity that we assume. So the black curves correspond to Kilonovae that were calculated using iron-like opacities, and in the red curves represent models that were calculated assuming that we had a lanthanide mass fraction of about 0.1. So as promised, when you have a higher opacity, you turn your light curve from a short peak into kind of a broader plateau, and you you also push the emission out into the infrared, both because you have extreme line blanketing in the optical and red wavelengths, and also because there's more time, by the time the radiation is diffused out, the system is cooled via adiabatic expansion, and so you just naturally produce a better spectrum that way. So these kind of represent, two cases that we might expect to be present in kilonova signals, depending on whether we have a very robust R process where the lanthanides are produced in large quantities, meaning about solar abundances, or a less successful R process that doesn't make it all the way up to the third peak and produce a lot of lanthanides and actinides. Okay, so now let's talk about data. This is I guess more of a qualitative picture of the signal that was seen, and I know we've seen a lot of data already, so this is probably pretty familiar by now. But this is showing sort of, let's see, both brightness and rough black body fits of the kilonova as observed by the various telescopes in the Las Cumbres Observatory network. And as we've discussed, we started out with something that was kind of bright blue, and then that emission faded away, and on later times we saw the rise of the red and the infrared emission. And so the simplest interpretation, based on the discussion that we've had about opacities, is that we're seeing some component of the ejecta that has fewer lanthanides at early times, and then as time goes on, maybe we see deeper into the ejecta, or another component is visible to us, and that component is more lanthanide rich, giving rise to this red ejecta. Okay, so based on this simple argument, we think we're approaching a somewhat coherent picture of what we might be seeing, or what we might have seen when we, and when I say we, I mean my observational colleagues, observed this system. So this is just a cartoon that I borrowed, showing these different kilonova components that we've heard of, right? So based on based on observations in a lot of different bands, we kind of have a rough idea that we're not right on the axis of rotation for the binary. We're somewhere a little bit off the axis. And then we imagine that the kilonova is composed of squeezed dynamical ejecta at the poles, along with some colder R process material, maybe around the edges, and then a very lanthanide rich and thus red disk wind situated in the interior. And so, this was our viewing angle, and this was the system we were looking at. We would first see the emission due to this lanthanide core material. And lanthanide core probably requires some some level of neutrino irradiation, which actually arises kind of naturally if you think about, arises naturally from a neutron star merger, because we expect some material to be squeezed out of the interface when the two neutron stars crash together. This material is really hot and shock heated, and it's easily able to produce neutrinos that could give you the irradiation required to drive the YE down and avoid producing the lanthanides that would cause the emission to be red instead of blue. So we heard in the last session that it's still a little bit tricky to explain not the blue quality of the ejecta, but just the quantity of emission that's required based on these earliest models to fit the data. There's still open debate there, but it seems like we're probably seeing some lanthanide core component at early times. But then that's moving very quickly, it's fading away. So if we wait long enough, we eventually can see into some more lanthanide-rich, redder material whose emission persists on much longer timescales. Okay, and I will just finish up with some nice movies. So this is showing sort of in very, very broad bands, right? Some blue and red emission based both on data and then based on some models that we built and published very recently, along with a corresponding picture of ejecta components that we expect to be contributing to the emission at each time. Or not. Okay. It sure did. Sorry, I'll imagine I've more or less run out of my time. So if you really want to see these, then I'm not able to.
Maybe Ben could start.
Should Ben start? Yeah.
Yeah. Why don't
okay.
we thank Jennifer and then. Maybe if you get to work, we can swing back. A question for Jennifer.
What is the dependence on the seed nuclei what you are using for the simulation? I assume it doesn't matter.
Yeah, I think it's pretty easy to make seed nuclei.
So it doesn't matter
and
when
to
to
make a
start
pretty
with.
broad distribution anyway. So I don't think that's a major. I don't know. We have some R process experts in the audience, so if someone wants to give a more detailed answer, I do.
The one difference from what Jim discussed, which the original models kept the matter really cold, and you formed the seed nuclei as a part of this sort of decompressing process. Most of the matter that's ejected, we think, in the simulations now is so hot that it's initially in nuclear statistical equilibrium and expands, and you sort of create these nuclei naturally through just normal nuclear fusion. I mean, it's very fast. So I think it's pretty independent of what you start with. Basically, all the protons get gobbled up, and that sets your seed nucleus. Okay, great. Any other questions?